Now that we have superposition and phasors, we're able to analyze a circuit where you have multiple sinusoidal inputs. As a reminder, what superposition says that if I have a circuit where there are multiple sinusoidal inputs, what I do is I treat that as n separate problems. Each problem has a single sinusoidal input, which I can solve using phasor analysis. I then solve those n problems separately, and then add up the answers to get the total output. So that's all fine and dandy, but here's a problem. Suppose the input is not a sine wave. A typical engineering solution is if you have a problem that's difficult to solve, change the problem so that it is solvable. Here what we're going to do is if the input is not a sine wave, we're going to change the problem so that the input is a sine wave. The advantage is by doing so, the problem's solvable, but we want to do it in a way so that we keep the flavor of the original problem, so that our answer is close and meaningful. The specific example I want to cover is this is an AC to DC converter that we'll be covering in ECE 320 Electronics 1. What I want to do is determine the voltage at V2. This circuit right here is a full wave rectifier. From our standpoint, what we care about is that the sine wave is rectified. So I have the positive half of the sine wave and the negative half that's been rectified. So this is what V1 looks like. The problem here is that V1 is not a sine wave, but I'd like to find what V2 is in spite of the fact that V1 is not a sine wave. So what we're going to do is the typical engineering solution. Let's change the problem. Let's come up with a different V1 that is a sine wave, hence I can solve it, but keeps the flavor of the original problem. By keeping the flavor, what I mean is that V1 has the DC level as an average. Make the new fictitious V1 have the same DC level. It's also got a time-varying signal, that's your ripple. Keep the same frequency, this is 120 Hz for the ripple, and it has a peak-to-peak value of 19.3 volts. So let's come up with a new V1 that is a sine wave, has the same DC value, same frequency for the AC part, and same peak-to-peak voltage for the AC part. So what we'll do is pretend the red line is actually V1. It's actually got a DC term, same DC term as the blue V1, an AC term. It's got the same frequency, same peak-to-peak voltage, it's almost the same input. There's a slight difference in the phase shift, but for AC to DC converters, I don't really care about the phase shift, I just care about the ripple. So, now that I have the input as a constant and a sine wave, this is the constant 11.31 volts, same as the actual V1. This has the 19.3 volt ripple, peak to peak, and the frequency is 120 Hz. Now let's analyze this. From superposition, I've got a DC term, analyze that, and a 120 Hz term, analyze that separately. At DC, the input is just 11.31, the frequency is 0, so going back to our circuit, I just have a voltage divider. 100 ohms over 100 plus 30 times V1. And I get 8.70 volts. Now let's analyze the circuit at 120 Hz. For the AC part, at 120 Hz the inductor becomes J754 ohms, the capacitor becomes 1 over J omega C minus J132 ohms. The input is a 19.3 volt peak-to-peak sine wave. The output then, by voltage division, is what I'm measuring. Putting these together, that's 63 minus J48 ohms, R1 over R1 plus R2, times the input, gives you 2.16 volts peak to peak. Again, the angle I ignored, I just care about the amplitude. That's how much V2 is rippling. Put the two together, the DC and the AC part, what I get is the DC part should be 8.7 volts with a 2.16 volt peak to peak ripple. If you simulate in Circuit Lab, or Part Sim, pick your favorite circuit simulator, you'll get the actual output. The actual output has about the same DC value and about the same ripple. The ripple's a little bit off because what we assumed is a little bit wrong, but it's close. Oftentimes electronics, it's close. Plus I was able to analyze it to get the right answer. We get an answer that's close. That's what we do in electronics. Change the problem to a DC term and an AC term, the first harmonic, and then analyze the circuit, you'll get an answer that's close. If you want to get more accurate, throw the circuit in simulation. Second example. Suppose I have a buck converter. This is another circuit that we cover in electronics. Here what I have is a 20 volt source. If I close the switch, I'll have 20 volts going to the load. If I open the switch, I'll have 0 volts going to the load. By chattering the switch on and off, I can make the average voltage going to V2 something between 0 and 20. That's called a buck converter. Suppose, for example, I have 80% modulation, meaning this is closed 80% of the time, open 20%, and I'm switching at 1 kilohertz. That means V1 is fairly easy to find. V1 is 20 volts 80% of the time, and it'll be off 0 volts, actually it's going to be minus 0.7 volts for the other 20%. And V1 is not a sine wave. That makes the circuit hard to analyze. So what we're going to do is change the problem. This is what V1 looks like. It's got a DC term. It has a 1 kilohertz time varying signal. And the peak-to-peak voltage is 20.7 volts. So let's pretend that the input has the same DC value, 15.86 volts, and a 20.7 volt peak-to-peak ripple at 1 kilohertz. Pretend this is the input. Again, I'm changing the problem, changing it so that the problem is solvable, but keeping the flavor of the original problem. For this new problem, I can do the DC analysis. DC voltage is just 13.2 volts. I can do the AC analysis. It's just convert the inductor capacitor to the impedance, solve for the input, which is now 20.7 volts peak to peak. I get the output. Put the two together. I've got a DC signal plus a little bit of ripple. And if you compare what we calculated to the actual, the calculations are fairly close. I've got the correct DC value. I slightly overestimated the ripple. But again, oftentimes that's close enough. If I want to get more accurate readings, I can simulate it like we did here. Or we can use another technique called Fourier transforms. It's a more accurate way to analyze the circuit, way more complicated, but you get slightly more accurate answers. That we'll cover next. So in summary, by changing the problem to include a DC offset and a sine wave, you're able to get answers that are very, very close. You're able to solve for V2, and without changing significantly the answers, our answers are reasonably close. Going to get closer, simulate the circuit.